Hello friends, welcome to our YouTube channel. Two-port networks may be described in various ways. Today we shall learn how to describe a two-port network using short-circuit admittance parameters or simply Y parameters. We shall learn how to draw the equivalent circuit of a two-port network using Y parameters. We shall see how to determine these Y parameters. Finally, we shall solve a couple of numerical problems to learn how to determine Y parameters for given two-port electrical networks. An electrical network having one input port and one output port is known as two-port network. Here we can see the block diagram of a two-port network. By analogy with transmission networks, one of the port is termed as input port and the other is called the output port. Each port contains two terminals, one for entry and the other for exit. By definition of the port, current at the entry terminal of a port must be equal to that of the exit terminal. A two-port network deals with four variables, V1, I1 for the input port and V2, I2 for the output port. Only two of these four variables are independent. Therefore, any two variables can be expressed in terms of the other two. We use two linear equations to relate these variables. Short-circuit admittance parameters represent the relation between the port currents and the port voltages in the two-port network. That is, when we use short-circuit admittance parameters, we express input and output port currents I1 and I2 in terms of input and output port voltages V1 and V2. The linear equations used are I1 equals to Y11 V1 plus Y12 V2 and I2 equals to Y21 V1 plus Y22 V2. These two equations can be written in matrix form as follows. Matrix of I1, I2 equals to matrix of Y11, Y12, Y21, Y22 into matrix of V1, V2. Or simply we can write matrix of I equals to matrix of Y into matrix of V. The elements of the matrix Y are known as Y parameters. These parameters are measured by performing short-circuit test. That is why they are known as short-circuit admittance parameters. They are measured in mho. Now let us draw the equivalent circuit using Y parameters. The linear equations used to describe a two-port network using Y parameters are I1 equals to Y11 V1 plus Y12 V2 and I2 equals to Y21 V1 plus Y22 V2. We have to implement these two equations while drawing the equivalent circuit. Let us draw the input and output ports first and then assign the port voltages and currents. Now, if we look at the first equation, we can see it contains two parts. The first part, Y11 V1, can be implemented easily by connecting an admittance Y11 at the input port. Now, let us see the second part. It is nothing but a dependent current source controlled by the output port voltage V2. So let us draw a voltage controlled current source Y1 to V2. Now the first equation is satisfied. Let us scrutinize the second equation. It again contains two parts. The second part, Y2 to V2, can be implemented easily by connecting an admittance Y22 at the output port. If we have a look at the first part, it is nothing but a current source controlled by the input port voltage V1. So, to implement this, let us connect an voltage controlled current source. Now the second equation is satisfied. Hope you will now be able to draw the equivalent circuit using Y parameters. Now let us find the Y parameters. First, we shall connect a voltage source at the input port and we will short circuit the output port using an ammeter. Hence, V2 equals to 0. Now we shall connect an ammeter to measure input port current I1 and a voltmeter to measure the input port voltage V1. The linear equations used to describe a two-port network using Y parameters are I1 equals to Y11 V1 plus Y12 V2 and I2 equals to Y21 V1 plus Y22 V2. When V2 equals to 0, the first equation reduces to I1 equals to Y11 V1. Therefore, we get Y11 equals to I1 by V1. Y11 is termed as driving point admittance at port 1 or short circuit input admittance. When V2 equals to 0, the second equation reduces to I2 equals to Y21 V1. Therefore, we get Y21 equals to I2 by V1. Y21 is termed as forward transfer admittance. Both Y11 and Y21 are measured in mho. Now let us determine the other two parameters Y12 and Y22. For this purpose, we shall connect a voltage source at the output port and we shall short circuit the input port using an ammeter. So V1 equals to 0. We shall measure the output port current I2 using an ammeter and the output port voltage will be measured by a voltmeter. The linear equations used to describe a two-port network using Y parameters are I1 equals to Y11 V1 plus Y12 V2 and I2 equals to Y21 V1 plus Y22 V2. When V1 equals to 0, the first equation reduces to I1 equals to Y12 V2. Therefore, Y12 equals to I1 by V2. It is termed as reverse transfer admittance. When V1 equals to 0, the second equation reduces to I2 equals to Y22 V2. Therefore, we get Y22 equals to I2 by V2. This is termed as driving point admittance at port 2 or short circuit output admittance. Both Y12 and Y22 are measured in mho. Now we shall solve a couple of numerical problems. First, we shall find Y parameters for the pi network shown. Let us assign input and output port voltages as V1 and V2 and identify the nodes 1 and 2. Now we shall apply Kirchhoff's current law at node 1 and we get I1 equals to YA plus YC times V1 minus YC times V2, and applying Kirchhoff's current law at node 2 we get I2 equals to minus YC times V1 plus YB plus YC times V2. The linear equations we use to describe a two-port network using Y parameters are I1 equals to Y11 V1 plus Y12 V2 and I2 equals to Y21 V1 plus Y22 V2. By comparing these two sets of equations, we get Y11 equals to YA plus YC, Y12 equals to Y21 equals to minus YC and Y22 equals to YB plus YC. Now let us determine the Y parameters for the resistive pi network shown. We know for a generalized pi network comprising of YA, YB, YC, Y11 equals to YA plus YC, Y12 equals to Y21 equals to minus YC, Y22 equals to YB plus YC. By comparing these two networks, we observe YA equals to 1 by 4, that is 0.25 mho, YB equals to 1 upon 8, that is equal to 0.125 mho, YC equals to 1 upon 2, that is 0.5 mho. Therefore, we can write Y11 equals to YA plus YC equals to 0.25 plus 0.5, that is equal to 0.75 mho. Y12 equals to Y21 equals to minus YC, that is equal to minus 0.5 mho. Y22 equals to YB plus YC, that is equal to 0.125 plus 0.5, that is equal to 0.625 mho. Now let us derive y parameters for the pi network shown. We know for any generalized pi network comprising of ya, yb, yc, y11 equals to ya plus yc, y12 equals to y21 equals to minus yc, and y22 equals to yb plus yc. By comparing these two pi networks, we observe ya equals to 1 upon minus j5, that is equal to j.2 mho, yb equals to 1 by 5, that is equal to 0.2 mho, yc equals to 1 upon 10 plus j5, that is equal to 0.08 minus j.04 mho. Therefore, y11 equals to 0.08 plus j.16 mho, y12 equals to y21 equals to minus 0.08 plus j.04 mho, y22 equals to 0.28 minus j.04 mho. Let us derive y parameters for the bridged T network shown. First, we assign input and output port voltages and currents. Let's identify the nodes 1, 2 and 3. The capacitive branch offers impedance Z equals to minus jXc equals to 1 upon j omega c, that is equal to 1 by Sc, where S equals to j omega. Applying Kirchhoff's current law at node 1, we get I1 equals to V1 minus V3 by 1 plus V1 minus V2 by 1 by 0.5 S. Simplifying, we get 0.5 into S plus 2 V1 minus 0.5 S V2 minus V3. Applying Kirchhoff's current law at node 2, we get I2 equals to V2 minus V3 by 0.5 plus V2 minus V1 divided by 1 by 0.5 S. Simplifying, we get minus 0.5 S V1 plus 0.5 into 4 plus S V2 minus 2 V3. Applying Kirchhoff's current law at node 3, we get 0 equals to V3 minus V1 by 1 plus V3 minus V2 by 0.5 plus V3 by 1 by S. Simplifying, we get V3 equals to V1 plus 2V2 divided by S plus 3. So now we have three equations. I1 equals to 0.5 times S plus 2 V1 minus 0.5 S V2 minus V3. I2 equals to minus 0.5 S V1 plus 0.5 into 4 plus S V2 minus 2 V3. and the third equation is V3 equals to V1 plus 2V2 divided by S plus 3. When we short circuit the output port, that is V2 equals to 0, the third equation gives us V3 equals to V1 divided by S plus 3. Using this expression in first equation, we get I1 equals to 0.5 S plus 2 V1 minus V1 by S plus 3. That is equal to S square plus 5S plus 4 divided by 2 into S plus 3 times V1. That gives us Y11 equals to I1 by V1 equals to S square plus 5S plus 4 divided by 2 into S plus 3 more. Now, using the expression of V3 from equation 2, we get I2 equals to minus 0.5 S V1 minus 2 V1 by S plus 3, that is equal to minus of S square plus 3S plus 4 divided by 2 into S plus 3 times V1. Therefore, Y21 equals to I2 by V1 equals to minus of S square plus 3S plus 4 divided by 2 into S plus 3 more. When we short circuit the input port, that is V1 equals to 0, from equation number 3 we get V3 equals to 2V2 by S plus 3. By using this expression in equation number 1, we get I1 equals to minus 0.5 S V2 minus 2V2 by S plus 3, that is equal to minus S square plus 3S plus 4 divided by 2 into S plus 3 V2. Therefore, we get Y12 equals to I1 by V2, that is equal to minus S square plus 3S plus 4 divided by 2 into S plus 3 more. Using the expression of V3 in equation number 2, we get I2 equals to 0.5 into 4 plus S V2 minus 2 into 2 V2 by S plus 3, that is equal to S square plus 7S plus 4 divided by 2 into S plus 3 V2. Therefore, we get Y22 equals to I2 by V2, that is equal to S square plus 7S plus 4 divided by 2 into S plus 3 more. So, today we have learned how to describe a two-port network using Y parameters. We have learned how to draw the equivalent circuit using Y parameters, and we have observed how to determine these Y parameters performing short circuit tests at input and output ports. Finally, we have solved a couple of numerical problems to determine Y parameters for given electrical networks. That's all I have for you today. Hope this lecture has been useful for you. If you have any question or suggestion, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.